The blizzard hit the trading post on the third night of March 1819, driving snow horizontally across the barren lands with winds that made standing impossible. Inside the log cabin that served as Hudson's Bay Company's northernmost outpost, we fed the iron stove continuously, split spruce every 20 minutes, and still the temperature barely held above freezing. Ice formed on the interior walls where our breath condensed. The wind found every gap between logs, every imperfect chinking, and exploited it ruthlessly. We were miserable, and we were supposedly sheltered. The Inuit elder who traded with us, a man named King Whack, had built his shelter 300 yards from our cabin, in full view across the frozen lake. When the blizzard started, I assumed he'd seek refuge in our cabin. Any sensible person would abandon a structure made of snow in favor of solid wood walls and an iron stove. But he didn't come. Through the brief clearing on the morning of the fourth day, I could see smoke rising from a small hole in his snow dome, a thin, steady column that indicated warmth and life. I left the cabin dressed in every layer I owned, wool, fur, leather, and crossed the lake on foot. The wind had died to perhaps 20 miles per hour, down from 50 the night before. But the temperature was minus 35 Fahrenheit, cold enough that my breath froze in my beard within seconds. I approached King Whack's shelter, what I later learned to call an igloo, from the Inuktitut word igloo meaning house, expecting to find him huddled and suffering, waiting out the storm. I called out, announced myself. King Whack's voice came from inside, calm, inviting me to enter. I found the entrance tunnel, a low passage, maybe 4 feet long, and crawled through on hands and knees. The tunnel descended below the snow surface, then rose up into the main chamber. When I emerged into the interior space, I stopped, stunned by what I was experiencing. Warmth, not hot, not even what I'd call comfortable by cabin standards, but noticeably, distinctly warmer than outside. I pulled off my mittens, something I hadn't been able to do outside, and held my bare hands in the air. The air temperature was perhaps 30 degrees, maybe 35, 60 to 65 degrees warmer than the exterior. And this warmth was maintained with no fire, just 2 small seal oil lamps burning quietly on either side of the sleeping platform. King Whack sat cross-legged on a platform of snow covered with caribou hides, wearing a light parka, working on repairing a harpoon line. He looked comfortable, relaxed, entirely at ease in a structure built from frozen water while a blizzard raged outside. He smiled at my visible surprise, gestured for me to sit, and continued his work. I sat, trying to understand what I was experiencing. The walls around me were snow. I could see the individual blocks, each roughly 2 feet long, 18 inches high, 6 inches thick, fitted together in a continuous spiral that curved up to a dome peak perhaps 7 feet above the floor. The walls glowed softly, translucent, allowing diffuse light to penetrate from outside. One block, positioned low on the south-facing wall, was clearer than the others, lake ice rather than snow, creating a small window that admitted more direct light. The air was still, without the drafts that plagued our cabin. I could see my breath, but barely. The moisture wasn't condensing as rapidly as it did outside. The temperature was stable, not fluctuating with the wind gusts outside, and most remarkably, this warmth was being maintained by perhaps 600 BTUs per hour of heat input, the 2 lamps plus King Whack's body heat. Our cabin required perhaps 30,000 BTUs per hour from the stove to maintain barely freezing conditions. I'd been trained as an engineer before joining the company. I understood thermodynamics, heat transfer, insulation principles, but this igloo violated everything I thought I knew about winter shelter. Wood was a decent insulator, snow was frozen water, and ice conducted heat readily. A log cabin should be warmer than a snow dome. Yet here I sat, in demonstrable comfort, surrounded by walls of ice, while my colleagues suffered in a cabin of wood. King Whack watched me examine the structure, reading my confusion. He spoke limited English, but he understood my interest. He gestured to the walls, to the entrance, to the small vent hole at the dome's peak. He was offering to teach me, to show me how the igloo worked, why it succeeded where logic suggested it should fail. I spent 9 days living with King Whack in his igloo, measuring, observing, learning. I documented every dimension, every technique, every principle that made the structure function. What I discovered challenged my assumptions about shelter, about insulation, about the relationship between material and thermal performance. The igloo wasn't primitive. It was sophisticated engineering, refined over centuries, optimized for extreme cold in ways European architecture had never considered. This is what I learned, how I came to understand that a wall of ice could be warmer than a wall of wood, that indigenous knowledge of physics could exceed what universities taught, that survival in the Arctic required not dominating the cold, but working with it in ways that seemed, at first encounter, impossible. The blizzard hit the trading post on the third night of March, 1819, driving snow horizontally across the barren lands with winds that made standing impossible. Inside the log cabin that served as Hudson's Bay Company's northernmost outpost, we fed the iron stove continuously, split spruce every 20 minutes, and still the temperature barely held above freezing. Ice formed on the interior walls where our breath condensed. The wind found every gap between logs, every imperfect chinking, and exploited it ruthlessly. We were miserable, and we were supposedly sheltered. The Inuit elder who traded with us, a man named King Whack, had built his shelter 300 yards from our cabin in full view across the frozen lake. When the blizzard started, I assumed he'd seek refuge in our cabin. Any sensible person would abandon a structure made of snow in favor of solid wood walls and an iron stove. But he didn't come. Through the brief clearing on the morning of the fourth day, I could see smoke rising from a small hole in his snow dome, a thin, steady column that indicated warmth and life. I left the cabin dressed in every layer I owned, wool, fur, leather, and crossed the lake on foot. The wind had died to perhaps 20 miles per hour, down from 50 the night before, but the temperature was minus 35 Fahrenheit, cold enough that my breath froze in my beard within seconds. I approached King Whack's shelter, what I later learned to call an igloo, from the Inuktitut word igloo, meaning house, expecting to find him huddled and suffering, waiting out the storm. I called out, announced myself. King Whack's voice came from inside, calm, inviting me to enter. I found the entrance tunnel, a low passage maybe 4 feet long, and crawled through on hands and knees. The tunnel descended below the snow surface, then rose up into the main chamber. When I emerged into the interior space, I stopped, stunned by what I was experiencing. Warmth, not hot, not even what I'd call comfortable by cabin standards, but noticeably, distinctly warmer than outside. I pulled off my mittens, something I hadn't been able to do outside, and held my bare hands in the air. The air temperature was perhaps 30 degrees, maybe 35, 60 to 65 degrees warmer than the exterior. And this warmth was maintained with no fire, just 2 small seal oil lamps burning quietly on either side of the sleeping platform. King Whack sat cross-legged on a platform of snow covered with caribou hides, wearing a light parka, working on repairing a harpoon line. He looked comfortable, relaxed, entirely at ease in a structure built from frozen water, while a blizzard raged outside. He smiled at my visible surprise, gestured for me to sit, and continued his work. I sat, trying to understand what I was experiencing. The walls around me were snow. I could see the individual blocks, each roughly 2 feet long, 18 inches high, 6 inches thick, fitted together in a continuous spiral that curved up to a dome peak perhaps 7 feet above the floor. The walls glowed softly, translucent, allowing diffuse light to penetrate from outside. One block, positioned low on the south-facing wall, was clearer than the others, lake ice rather than snow, creating a small window that admitted more direct light. The air was still without the drafts that plagued our cabin. I could see my breath, but barely. The moisture wasn't condensing as rapidly as it did outside. The temperature was stable, not fluctuating with the wind gusts outside. And most remarkably, this warmth was being maintained by perhaps 600 BTUs per hour of heat input, the 2 lamps plus King Wax body heat. Our cabin required perhaps 30,000 BTUs per hour from the stove to maintain barely freezing conditions. I'd been trained as an engineer before joining the company. I understood thermodynamics, heat transfer, insulation principles. But this igloo violated everything I thought I knew about winter: shelter. Wood was a decent insulator, snow was frozen water, and ice conducted heat readily. A log cabin should be warmer than a snow dome. Yet here I sat, in demonstrable comfort, surrounded by walls of ice, while my colleagues suffered in a cabin of wood. King Wax watched me examine the structure, reading my confusion. He spoke limited English, but he understood my interest. He gestured to the walls, to the entrance, to the small vent hole at the dome's peak. He was offering to teach me, to show me how the igloo worked, why it succeeded where logic suggested it should fail. I spent 9 days living with King Wax in his igloo, measuring, observing, learning. I documented every dimension, every technique, every principle that made the structure function. What I discovered challenged my assumptions about shelter, about insulation, about the relationship between material and thermal performance. The igloo wasn't primitive. It was sophisticated engineering, refined over centuries, optimized for extreme cold in ways European architecture had never considered. This is what I learned, how I came to understand that a wall of ice could be warmer than a wall of wood, that indigenous knowledge of physics could exceed what universities taught, that survival in the Arctic required not dominating the cold, but working with it in ways that seemed, at first encounter, impossible. The third day, I watched King Wax begin constructing the new igloo. I'd seen stone architecture, understood how courses of stone or brick are laid horizontally, one complete layer, before starting the next. I expected igloo construction would follow the same pattern, circular courses stacked one atop the other. But King Wax's technique was entirely different and far more sophisticated than horizontal layering. He began by arranging blocks in a circle, marking out the igloo's footprint. The diameter was roughly 12 feet, large enough for a family of 4 or 5, small enough to heat with minimal energy. He placed the first course of blocks, perhaps 10 blocks total, creating the circular base. Then, instead of starting a second complete course, he cut a diagonal ramp into the top of 3 or 4 blocks, creating a gradually rising pathway. He placed the next block at the end of this ramp, 1 level higher than the base. The next block went beside it, also elevated. He continued, placing blocks, each one slightly higher than the previous, following the ramp he'd created. The structure wasn't rising in horizontal layers. It was rising in a continuous spiral, each block leaning slightly inward, each block supported by the blocks below and beside it. I watched the spiral develop. After one complete revolution, the wall had risen perhaps 18 inches and had completed a full 360-degree circle. After 2 revolutions, the wall was 3 feet high, and the inward lean was becoming more pronounced. The blocks were no longer vertical. They were tilted inward at perhaps 70 degrees from horizontal, creating the beginning of the dome's curve. King Wax worked quickly, placing each block with minimal adjustment. He'd carved the blocks with the correct taper, so they naturally wanted to lean inward at the right angle. He'd cut them to the right size, so they fit the spiral's curve without gaps. Occasionally, he'd use his snow knife to shave a high spot or adjust an edge, but mostly the blocks fit immediately, locked into place by their own weight and geometry. I asked to place a block myself. He handed me one, gestured where it should go. I positioned it on the wall, but it didn't sit correctly. It rocked, had gaps on both sides. King Guac smiled, took the block, rotated it slightly, and set it again. Now it fit perfectly, bearing on the blocks below, touching the blocks beside. The difference between my placement and his was perhaps 2 degrees of rotation, barely visible, but critical for proper fit. The spiral technique created continuous compression throughout the structure. Each block pushed inward against its neighbors, and those neighbors pushed back, creating a ring of compression forces that grew stronger as the wall rose. Unlike horizontal courses, where each layer rests entirely on the layer below, the spiral distributed forces along the length of the wall, preventing any single joint from bearing excessive load. By afternoon, the wall had risen to shoulder height, perhaps 5 feet, and the inward lean was dramatic. The blocks were now angled 45 degrees from vertical, clearly curving toward what would become the dome's peak. But the structure was stable, self-supporting, requiring no internal scaffolding or temporary supports. The geometry alone provided all necessary strength. I examined the joints between blocks. King Guac had cut them to fit closely, with gaps of perhaps a 1/4 inch or less. These gaps would be filled later, not with additional snow packed from outside, but with loose snow sprinkled from inside, then smoothed. The loose fill would bond to the blocks, sealing air leaks while maintaining the wall's insulating properties. As the spiral approached the dome's peak, the blocks became smaller, cut to fit the decreasing circumference. King Guac was working from inside now, placing blocks from below, reaching up to position them. The final block, the keystone, though in a dome there's no single keystone, was a small piece carved to exactly fill the remaining hole. He positioned it, shaved its edges to fit perfectly, then pushed it up into place. The dome was complete. The structure had risen from nothing to finished dome in roughly 3 hours. No mortar, no fasteners, no complex tools, just snow blocks, a knife, and understanding of geometry and forces. The dome stood 7 feet high at the peak, self-supporting, locked together by compression forces that would grow stronger as the structure settled and the blocks centered together over the following days. That evening, I sat inside the completed but not yet occupied dome. No lamps, no body heat, just the structure itself, and measured the temperature differential. Outside, -28 degrees. Inside, -18 degrees. The structure alone, with no heat source, was providing 10 degrees of warming simply by blocking wind and providing a small amount of insulation. Once heat was added, once the structure was truly occupied, the performance would improve dramatically. On the 4th day, I became obsessed with understanding the microscopic structure of the snow blocks. I knew they were insulating well, the measurements proved it, but I needed to see why to understand what was happening at the level of individual ice crystals. King Guac found my interest amusing but indulged it, helping me extract a small sample from a block for detailed examination. I used a magnifying lens I'd brought from the trading post, the kind used for inspecting furs and examining trade goods. Under magnification, the snow block structure became visible. Individual ice grains, each roughly 1 to 2 millimeters across, bonded together at their contact points. Between the grains were voids, air spaces, tiny pockets where no ice existed, where air was trapped and immobilized. The structure resembled a 3-dimensional lattice or foam. The ice grains formed a skeletal framework, and the air filled the space between framework elements. The ice provided structural strength, preventing the material from collapsing. The air provided insulation, preventing heat from conducting through the material. Neither element alone would work. Both together created material with useful properties. I estimated the geometry of the pore structure. The air pockets were roughly spherical or polyhedral, ranging from half a millimeter to perhaps 3 millimeters in diameter. They were interconnected to some degree. Air could move slowly through the material, but the connections were small, restricted, preventing rapid air circulation. This was critical. If air could move freely through the blocks, convection would carry heat through, negating the insulation value. The ice crystal bonds were also visible under magnification. Where two grains touched, they weren't just resting against each other. They were partially fused, connected by ice bridges that had formed through sublimation, water molecules evaporating from one surface and redepositing on the adjacent surface, gradually creating solid connections. This sintering process strengthened the material over time, making a fresh-cut block structurally stronger after a few days than when first cut. I thought about the thermal pathway through the material. Heat would conduct through the ice grains. Ice is an excellent conductor, but then it would encounter an air gap. To cross the gap, heat would have to either conduct through the still air, very slow, or cause the air to circulate and carry heat by convection, prevented by the small pore size, or radiate across the gap, minimal at the temperatures involved. The air gaps were thermal barriers, forcing heat to take a long, tortuous path through the material. I calculated the effective R value of the snow blocks. 6 inches of snow at 30 pounds per cubic foot density has an R value of approximately 3.5 to 4.0 per inch, giving the 6-inch blocks an R value of 21 to 24. For comparison, 6 inches of wood has an R value of roughly 6. The snow was 4 times more insulating than wood, despite being made of ice. That afternoon, King Whack showed me something I hadn't expected. The blocks improved with time. A fresh-cut block examined under my lens showed distinct grains with minimal bonding. A block that had been part of the igloo wall for several days showed much more extensive bonding. The ice bridges between grains had grown, creating a more cohesive structure. The block was stronger, denser, but still highly insulating because the air pockets remained. The sintering process was temperature-dependent. At temperatures just below freezing, sublimation occurred rapidly, and blocks bonded together within hours. At temperatures well below freezing, like the -30 we were experiencing, the process was slower, but still progressed. The igloo walls were literally getting stronger every day, self-healing any small cracks or imperfections through natural ice crystal growth. I also learned that the block's insulating value improved with use. As people lived in the igloo, their body heat and lamp heat would warm the interior surface of the walls. This warming would cause slight sublimation on the inside surface, then recrystallization, gradually densifying the inner layer. Meanwhile, the outer layer remained cold and porous. The result was a density gradient, denser and thus stronger on the inside, more porous and thus more insulating on the outside. By evening, I understood that the igloo wasn't a static structure. It was dynamic, evolving, improving with time and use. The material itself was sophisticated, a carefully balanced composite of ice and air, structure and insulation, strength and lightness. The Inuit hadn't just discovered that snow could be used for building, they'd learned to select snow with specific properties, to cut and place it to maximize those properties, and to let natural processes improve the structure after construction. The 5th day, I focused on the entrance, the feature I'd crawled through without much thought on my first visit, but which I now recognized as critical to the igloo's thermal performance. The entrance wasn't a simple doorway. It was an engineered airflow management system that prevented cold air infiltration while allowing access. The entrance tunnel was roughly 4 feet long, excavated below the level of the igloo floor. From outside, you descended perhaps 2 feet down into the tunnel, crawled through the horizontal section, then ascended up through an opening in the igloo floor. The profile was U-shaped, down, across, up. This geometry was universal in every igloo I'd seen Kingwak build, and I needed to understand why. I started with basic physics. Cold air is denser than warm air. Dense air sinks. Light air rises. If the entrance were a simple horizontal tunnel at floor level, cold air from outside would flow directly into the igloo whenever the entrance was used, and warm air from inside would flow out. The U-shaped profile prevented this by creating a trap, a low point where cold air would pool and sit, unable to rise into the living space. I measured the dimensions carefully. The tunnel floor was 24 inches below the igloo floor level. The tunnel was perhaps 30 inches wide, barely enough to crawl through. The total length from outside opening to inside opening was 54 inches. The tunnel was carved from the same wind-compacted snow as the igloo blocks, creating an insulated passage rather than an open-air connection. To test the cold trap function, I used my thermometer at various points. Outside air temperature, minus 32 degrees. Temperature at the bottom of the entrance tunnel, minus 28 degrees. Temperature at the inside opening of the tunnel, at floor level, minus 10 degrees. Temperature in the living space, 3 feet above the floor, plus 32 degrees. The tunnel was creating a 42-degree temperature, gradient over a distance of just 4 feet. The gradient existed because cold air was pooling in the tunnel's low point, prevented from rising by its own density. Warm air from the living space couldn't descend into the tunnel because it was lighter, more buoyant, than the cold air below. The two air masses separated naturally, with the boundary layer at approximately floor level. I observed what happened when someone entered or exited. Kingwak crawled through the tunnel, disturbing the cold air, pushing some of it ahead of him. But within minutes of his entry, the cold air settled back down, re-established the trap, restored the temperature gradient. The disturbance was temporary. The system was self-correcting. The tunnel also functioned as an airlock in another sense. It was long enough that you couldn't be simultaneously exposed to both the outside environment and the interior environment. When you were in the tunnel, both ends were out of reach. This meant the entrance was never truly open in the sense of creating a direct path between inside and outside. There was always at least 4 feet of insulated tunnel between the two spaces. I thought about European architecture, about doorways and vestibules. We understood that doorways lost heat, so we built vestibules, enclosed porches or entryways that created a buffer zone. But even the best vestibule required 2 doors, required hinges and latches and maintenance. The igloo entrance tunnel achieved the same buffering function with no moving parts, no hardware, no maintenance, using only geometry and the natural behavior of cold air. That afternoon, I experimented with blocking the entrance tunnel. I used a block of snow to completely seal the tunnel at its midpoint, eliminating any air exchange between inside and outside. Within an hour, the air quality inside the igloo noticeably degraded. The air felt stuffy, heavy. Moisture was condensing excessively on the walls. I removed the block, and within 20 minutes, air quality improved. The tunnel allowed minimal but adequate air exchange, enough to maintain breathable air without excessive heat loss. The tunnel also served as a windbreak. Arctic winds can blow at 50, 60, even 70 miles per hour. Wind creates pressure on the windward side of structures, driving air infiltration. But the tunnel entrance, being below surface level and sheltered by drifted snow, was protected from direct wind. Wind couldn't drive cold air into the tunnel. Air could only enter by natural diffusion or by someone crawling through. By evening, I'd measured every dimension, mapped the temperature gradient, understood the physics. The cold trap entrance was elegant in its simplicity. Dig down, cross, come up. No complex engineering, no precise calculations required during construction. Just an understanding that cold air sinks, and if you force it to sink below your living space, it won't rise to bother you. On the sixth day, I turned my attention to the window, the single clear block I'd noticed on my first visit, positioned low on the south-facing wall. I'd assumed it was decorative or perhaps just a structural variation, but King Guac explained through gestures and broken English that it served specific purposes: light admission and solar heat gain. The window block wasn't made from snow, it was lake ice, cut from the frozen lake surface in late fall when the ice was perhaps 6 inches thick. Lake ice forms differently than snow. It freezes from liquid water in a relatively calm environment, creating clear or translucent ice with minimal air bubbles. This ice transmitted light much better than snow blocks, which were translucent but diffused light strongly. King Guac showed me where he'd harvested the ice block. He'd cut it from a location where the lake ice was clear, away from where snow had fallen on the ice and created opaque layers. He'd cut a rectangular block, roughly 18 inches by 12 inches by 6 inches, then carried it back and incorporated it into the igloo wall during construction. The ice block fit like any other block but served an entirely different function. I measured light transmission. Outside, the bright snow under clear sky provided intense illumination. Through the ice window, perhaps 30 to 40% of that light entered the igloo. Through the surrounding snow blocks, perhaps 5 to 10% entered. The ice window provided 3 to 4 times more light than an equivalent area of snow wall, enough to read by during daytime hours, enough to reduce dependence on seal oil lamps for illumination. But light wasn't the only function. The ice window also admitted solar radiation, infrared heat, as well as visible light. On days when the sun was out, even the weak winter sun at this latitude, I could feel warmth radiating from the ice block. I measured the surface temperature. Outside surface, minus 20 degrees. Inside surface, minus 5 degrees. The 15-degree differential meant heat was conducting through the ice block, from the sun-warmed outside surface to the inside surface, adding warmth to the igloo interior. I calculated the solar gain roughly. The window area was approximately 1.5 square feet. On a clear day, solar radiation at this latitude in winter might deliver 50 BTUs per square foot per hour. If the ice block transmitted 20% of that radiation, accounting for reflection and absorption, the window was adding roughly 15 BTUs per hour to the interior. Not substantial, but not negligible, either given the igloo's low heat requirements. The window position was carefully chosen. It faced south or slightly southeast, the direction of the low winter sun. It was positioned low on the wall, at floor level, where the sun's low angle would strike it directly, rather than being blocked by the dome's curve. If the window had been positioned higher, or on a different orientation, it would receive less direct sun, would contribute less light and heat. I wondered about thermal losses through the window. Ice conducts heat much better than snow, perhaps 20 times better, given the densities involved. A 6-inch thick ice block has an R value of maybe 3 compared to 21 for a snow block of the same thickness. The window was a significant thermal weak point, conducting heat out of the igloo faster than the surrounding walls. But King Guac had accounted for this. The window was small, only 1.5 square feet in a wall that was perhaps 250 square feet total. The heat loss through the window was roughly 10 BTUs per hour, significant but acceptable given the light and solar gain benefits. The Inuit had made a calculated trade-off: accept some heat loss in exchange for daylight and passive solar heating. That afternoon, I observed how the window affected daily life. During daylight hours, the ice window admitted enough light that lamps weren't needed for most tasks. This saved seal oil, a valuable resource that required significant effort to acquire. During sunny periods, the window provided noticeable warmth, warming the floor near the window, creating a slightly warmer microclimate in that area of the igloo. At night, the window became a liability, conducting heat away faster than the surrounding walls. But King Guac had a solution. He hung a caribou hide over the window after dark, creating an insulating layer that reduced heat loss. The hide wasn't perfect insulation, but it probably doubled the effective R value of the window assembly, cutting heat loss in half during the coldest nighttime hours. By evening, I understood that the ice window represented sophisticated resource management. Light and heat were valuable during the day. Insulation was valuable at night. The window provided day benefits, the hide cover reduced night costs. Together, they optimized the igloo's performance across the full daily cycle. The seventh day, I decided to quantify the heat balance, how much heat was entering the igloo, how much was being lost, and how those numbers balanced to create the comfortable interior temperature I'd been experiencing. I needed to understand whether body heat alone could truly maintain warmth, or whether I was missing some other heat source. I started with heat inputs. King Guac and I were the igloo's sole occupants. Each human body generates roughly 300 BTUs per hour at rest, more during activity. 2 people, 600 BTUs per hour from body heat. The 2 seal oil lamps burning continuously consumed perhaps a quarter pound of oil per day each. Seal oil contains roughly 9,000 BTUs per pound, so each lamp provided roughly 2,250 BTUs per day, or about 94 BTUs per hour. Total heat input, approximately 600 plus 188, equals 788 British thermal units per hour. Next, heat losses. The igloo had roughly 250 square feet of wall area with an average R value of 21. The temperature differential was roughly 60 degrees Fahrenheit, inside at 32 degrees, outside at minus 28. Heat loss through walls, 250 times 60 divided by 21 equals 714 BTUs per hour. The ice window added roughly 10 BTUs per hour loss. The entrance tunnel and ventilation hole added perhaps another 50 BTUs per hour. Total heat loss, approximately 774 BTUs per hour. The numbers nearly balanced, 788 BTUs per hour input versus 774 BTUs per hour loss. The slight surplus explained why the interior temperature was stable or slowly rising rather than falling. The igloo was achieving thermal equilibrium with minimal heat input, maintaining livable conditions through geometry and insulation rather than through massive heat generation. I compared this to the trading post cabin. The cabin required roughly 30,000 BTUs per hour from the stove to maintain barely freezing interior temperature. The igloo required only 788 BTUs per hour, less than 3% of the cabin's requirement. The difference was primarily insulation. The igloo's walls were 4 times more insulating than the cabin's log walls, and the igloo had no large openings like windows and doors that created major heat loss points. But there was more to the efficiency than just insulation. The igloo shape, a dome, minimized surface area relative to volume. A dome encloses the maximum volume with the minimum surface area, meaning less wall area through which heat can escape. The cabin, being rectangular, had higher surface area for equivalent volume, meaning more heat loss area. I calculated the volume to surface area ratio. The igloo, with a 12-foot diameter and 7-foot height, had roughly 528 cubic feet of volume and 250 square feet of surface area. Ratio, 2.1 cubic feet per square foot. The cabin, roughly 20 by 16 feet with 8-foot walls, had roughly 2,560 cubic feet of volume and 1,920 square feet of surface area, including floor and ceiling. Ratio, 1.3 cubic feet per square foot. The igloo's geometry was 60% more efficient at enclosing volume with minimal surface. That afternoon, I experimented with heat input variations. I extinguished one of the seal oil lamps, reducing heat input by roughly 90 BTUs per hour. Within 2 hours, the interior temperature had dropped from 32 degrees to 28 degrees. A 4-degree drop, enough to notice, but not enough to create discomfort. The igloo was sensitive to heat input changes, but not dramatically so. The thermal mass of the snow walls buffered the change, preventing rapid temperature swings. I also observed the heat distribution. The warmest air collected near the dome's peak, as expected. But even the floor, the coolest part of the interior, remained near 25 degrees, still well above outside temperature, still tolerable. The small heat input was sufficient because the excellent insulation prevented rapid heat loss, because the compact geometry minimized loss area, and because the thermal mass smoothed out fluctuations. By evening, I understood why the igloo worked with such minimal heat input. The structure wasn't fighting the cold through brute force heat generation. It was minimizing heat loss through insulation, geometry, and careful design. The body heat and small lamps provided just enough input to balance the losses, creating stable conditions with remarkable efficiency. On the 8th day, I focused on the ventilation hole, a small opening at the dome's peak, perhaps 3 inches in diameter, that I'd noticed, but not yet studied carefully. I'd assumed it was for smoke exhaust, but the seal oil lamps produced minimal smoke, so there had to be additional purpose. King Wack explained, the hole was for breathing, for air quality, for preventing carbon dioxide accumulation. I measured the hole size precisely, roughly 2.5 inches in diameter, giving an area of approximately 4.9 square inches or 0.034 square feet. This seemed remarkably small for ventilating a 528 cubic foot space occupied by 2 people, but King Wack insisted it was correct, too large, and the hole would exhaust too much warm air, too small, and air quality would degrade. The size was calibrated through generations of experience. To understand the airflow, I lit a small piece of moss and held it near the ventilation hole. The smoke was drawn upward, pulled out of the hole by the slight negative. Pressure created when warm air inside the igloo was lighter than cold air outside. The pressure differential was tiny, unmeasurable with my instruments, but sufficient to create gentle upward airflow. I calculated the air exchange rate roughly. If air moved through the 0.034 square foot opening at, say, 20 feet per minute, a barely perceptible flow, the volumetric exchange rate would be 0.68 cubic feet per minute, or about 41 cubic feet per hour. The igloo volume was 528 cubic feet, so complete air exchange would occur every 13 hours. This was remarkably slow compared to most buildings, which exchange air much more rapidly through infiltration and ventilation. But slow exchange was appropriate given the occupancy. 2 people produce roughly 0.3 cubic feet per minute of carbon dioxide. The ventilation hole was exhausting 41 cubic feet per minute, of which perhaps 0.4% was carbon dioxide, the atmospheric concentration plus what people exhaled. The CO2 removal rate was adequate to prevent accumulation, adequate to maintain breathable air, but not excessive enough to waste heat. I thought about the entrance tunnel's role in the ventilation system. The tunnel allowed fresh air to enter at floor level, drawn in by the negative pressure created when warm air exited through the top vent. The entering cold air was denser, sank to the floor, gradually warmed as it mixed with the interior air, then rose and eventually exited through the top. The igloo had a natural convection-driven ventilation system that required no fans, no mechanical assistance. That afternoon, I experimented with blocking the ventilation hole. I used a piece of hide to completely seal it, eliminating the exhaust path. Within an hour, the air inside felt different, heavier, more humid, slightly stale. Moisture was condensing more rapidly on the walls as the exhaled water vapor had nowhere to escape. The lamp flames burned less vigorously, indicating reduced oxygen levels. After 90 minutes, I was developing a mild headache, not dangerous, but uncomfortable. I removed the blockage, and within 20 minutes, air quality improved noticeably. The lamp flames brightened. The heavy feeling dissipated. Moisture condensation slowed. The ventilation hole's small size was deceptive. Its impact on livability was substantial. Without it, the igloo would be airtight, and the space would quickly become unbreathable. I also learned that the hole size was adjusted seasonally and based on occupancy. For a larger igloo with more people, the hole would be larger, perhaps 4 or 5 inches in diameter. In extremely cold conditions, the hole might be partially restricted to reduce heat loss, accepting slightly degraded air quality in exchange for warmth. The system was tunable, adjustable, based on immediate needs. By evening, I understood that the ventilation hole completed the igloo's environmental control system. The walls provided insulation. The entrance trap prevented cold air infiltration. The ice window admitted light and solar gain, and the ventilation hole maintained air quality while minimizing heat loss. Each element served a specific function, and together they created a livable environment from materials and geometry alone. The 9th day brought an observation that had been developing slowly. The interior surface of the igloo walls had changed over the week. When I first entered, the walls were slightly rough, showing the individual crystals of the snow blocks. Now, a week later, the walls were smooth, slightly glossy, with a thin layer of ice coating the interior surface. This glazing wasn't deterioration, it was improvement, intentional, or at least understood and welcomed. I examined the glaze carefully. It was perhaps 1/16 of an inch thick, clear to translucent ice that had formed from water vapor in the interior air. The vapor, from breathing, from the lamps, from any moisture sources, had migrated to the cold wall surface, condensed and frozen, gradually building up a continuous ice layer that sealed the joints between blocks and filled any small gaps or cracks. The glazing process was continuous. As we occupied the igloo, as we breathed and the lamps burned, we added moisture to the air. That moisture had to go somewhere. Some exited through the ventilation hole, but much of it condensed on the walls, the coldest surfaces in the space. Over days, the accumulated condensate created a complete ice shell on the interior. I thought about the thermal implications. The ice glaze was denser than the snow blocks, solid ice rather than snow's air-ice mixture. Ice conducts heat better than snow, so at first thought, the glaze should reduce the wall's insulating value. But the glaze was thin, much thinner than the 6-inch blocks, and it served a critical function. It sealed air leaks. Fresh-cut snow blocks, even when fitted carefully, have small gaps at the joints, tiny cracks where air can infiltrate. Air infiltration bypasses insulation, carrying heat directly through the wall via convection. The ice glaze sealed these infiltration paths, converting the wall from a collection of individual blocks to a continuous, airtight shell. The slight reduction in insulation value from the ice layer was more than compensated by eliminating air infiltration. I measured the temperature of the glazed interior surface. Roughly 28 degrees Fahrenheit, just below freezing. This temperature was critical. If the interior was warmer, above freezing, the glaze would melt and drip, creating a wet environment. If significantly colder, the glaze would build up too thickly, reducing insulation substantially. At just below freezing, the glaze stabilized at minimal thickness while still providing the sealing function. Kingwak explained that the glazing process was expected, welcomed, managed. In the first days of a new igloo's occupancy, the walls would glaze quickly. After the initial glaze formed, the rate would slow, with only minor additions as time passed. If the interior became too warm from too many people or too much fire, the glaze would melt and moisture would drip. This was a signal to reduce heat input, to adjust the ventilation, to maintain the proper thermal balance. That afternoon, I understood that the glazing process represented another form of thermal optimization. The igloo wasn't a static structure built once and done. It was a dynamic system that improved with use. The initial construction provided good insulation and structure, but the glazing process refined the thermal envelope, sealed leaks, improved performance beyond what construction alone could achieve. The glazing also made the igloo brighter inside. The smooth, slightly reflective ice surface reflected lamplight more effectively than the matte snow surface had. The same lamp provided better illumination after glazing than before, another small benefit of the occupancy process. By evening, I'd observed every stage of the igloo's thermal evolution: construction with carefully selected blocks, settling and sintering as blocks bonded together, glazing as moisture sealed the interior surface. Each stage improved performance, refined the structure, optimized the thermal envelope. The igloo reached its full potential not immediately after construction, but days later, after the occupant's presence had completed the finishing process. The 10th day, my time with Kingwak was ending. I documented everything measurable: dimensions, temperatures, densities, heat flows. I'd learned the construction techniques, understood the material properties, calculated the thermal performance. But more than technical knowledge, I'd gained understanding of a different approach to survival, a different philosophy of shelter in extreme cold. The igloo succeeded because it minimized rather than maximized. European winter shelter philosophy was about generating massive heat to overcome losses: huge fireplaces, thick walls to contain the heat, constant fuel consumption. The igloo philosophy was about minimizing losses so that minimal heat input would suffice. The difference was profound, both practically and conceptually. I reviewed my calculations one final time. The igloo maintained a 60-degree temperature differential, inside at 32 degrees, outside at -28, with only 788 BTUs per hour of heat input. The trading post cabin maintained a 30-degree differential, inside at 30 degrees, outside at 0, with roughly 30,000 BTUs per hour input. The igloo was achieving double the temperature differential with less than 3% of the heat input. This was efficiency at a level European architecture hadn't approached. The efficiency came from multiple strategies working together. Material strategy used snow blocks with optimal density, maximizing trapped air while maintaining structure. Geometric strategy: build a dome, minimizing surface area relative to volume. Entry strategy: create a cold trap, preventing infiltration while allowing access. Ventilation strategy: provide minimal but adequate air exchange. Thermal mass strategy: allow internal glazing to seal air leaks and refine the envelope. Each strategy alone would provide modest benefit. Together, they created a structure that could maintain livable conditions in the harshest environment on Earth, with heat input barely exceeding human body heat. This was engineering at its finest, not impressive because it used advanced materials or complex systems, but impressive because it achieved extraordinary results with minimal resources. I thought about what this meant for survival. The Inuit lived in an environment where fuel was scarce, driftwood rare, seal oil precious, every BTU valuable. They couldn't afford European-style heating that consumed vast quantities of fuel. They had to create shelter that worked with minimal heat, that leveraged insulation and geometry rather than combustion. The igloo was the solution refined over millennia, optimized through countless iterations, perfected through the survival pressure of Arctic winter. That afternoon I sat with Kingwak one final time, attempting to express what I'd learned. My language was inadequate. How do you explain in broken English and gestures that someone's traditional shelter represents thermal engineering more sophisticated than anything taught at European universities? that the physics embodied in the igloo would take European science another century to fully understand and quantify? King Whack smiled, nodded, gestured at the igloo around us. He didn't need my validation. He knew the igloo worked. His ancestors had known it for generations beyond counting. The igloo kept them alive, comfortable, safe through winters that would kill any unprepared person within hours. That was all the proof needed. As I prepared to leave, to return to the trading post cabin that suddenly seemed crude and inefficient, I understood something fundamental. Technology isn't about complexity or materials or tools. Technology is about solving problems effectively with available resources. By that measure, the igloo was more advanced than the cabin, more sophisticated than the iron stove, more elegant than anything European civilization had brought to the Arctic. The wall of ice that kept King Whack warmer than our log cabin did so through physics, trapped air insulation, minimal surface area geometry, cold air trapping, strategic sealing, and calculated ventilation. Each principle was simple, observable, understandable. But the combination, refined through generations of observation and improvement, created performance that seemed impossible at first encounter. I carried my journals and measurements back to the trading post, back to the cabin where we burned spruce logs by the armload and still suffered from cold. I would document what I'd learned, would try to explain to anyone who would listen that indigenous peoples of the Arctic had mastered thermal engineering while Europe was still building drafty castles. I would argue that we had much to learn from people we'd dismissed as primitive. But mostly I would remember the lesson of the igloo, that wisdom can come from any source, that survival refines knowledge to its essence, and that the best solutions often come not from adding complexity, but from understanding and working with fundamental principles. The igloo taught me humility, respect for knowledge outside my tradition, and appreciation for the intelligence embedded in every traditional technology that has sustained human life in extreme environments. The Inuit had survived Arctic winters for thousands of years before Europeans arrived. They'd survived not through luck or chance, but through knowledge of snow, of heat transfer, of geometry, of thermal balance. That knowledge, embodied in the igloo, represented a peak achievement of human adaptation to environment. And I'd been privileged to observe it, measure it, learn from it, and carry that understanding forward.